I'm reviewing some of this Elliott Sound products, articles, and just going through it to see, because this guy's been around. He's like 75 years old or something. I mean, he's been around for a long time. He knows a lot. Just trying to see if he knows anything that I don't, because I'm sure he does. But anyway, um, this discusses right here. This has this little footnote about ambient temperature. So you can kind of read here what he says about it. Um, but what I got to interject something, and this is my opinion, but I think if you think through what ambient temperature actually means in terms of an electronic component, if you just think through it logically, it'll make sense to you as to where you should take a temperature measurement. This guy's still vague about it, and I've just never really seen a formal definition for it. The best thing to do is just think through logically what it means when somebody, tells you what the ambient temperature is around an electronic component. Um, like here they're talking about resistors, and this is true. You really power resistors and even regular resistors, they really do or should be derated depending upon, your environment too, especially if you're pushing them to their limits. Um, but if you think about it, okay, a traditional like resistor, all right, is going to be mounted. It's on your circuit board. Now the question is what's its orientation, right? So, if it's mounted vertically or horizontally or what have you, you need to think about, well, for its operating temperature, what's taking place here? Because we all know heat rises, right? So you would not really want to take the temperature of the component on top of the component or near the component on top, because that's not the cooling air, okay? That's the heated air that's rising from the component. Now, you wouldn't want to just take it at a random location inside your enclosure, because that may not be the air that's actually cooling your components. Because, most enclosures will have dead zones in them, right? Areas that, can actually remain, almost isothermal, they might gradually heat up eventually. But that's not what the air that's going to directly cool your component is. Now, you wouldn't want to take it at the vent, where cool air is being drawn in at, like below it, because, that's still not close enough to the component. That's still relatively cool air. That hasn't even maybe come, it may have to go through 100 circuit boards, to get to your component. What you really need to take your temperature, at is right by the component, but it should be underneath the component, and especially if it's mounted on, a vertical circuit board, so you can imagine a resistor or some other component, take the temperature directly under the component. But my advice would be, if I were doing it, I would take it, like a few millimeters underneath. And that's the big question, how close, because, you do get radiative emissions, especially from real hot components. So, but you're mostly interested in the temperature of the air. So, I mean, I would say, anywhere from, maybe a quarter of an inch or so below the component. Like maybe 10 millimeters or 5 millimeters might be getting a little close. But what you're really interested in is what's the temperature of the air that's being drawn into the convection plume of the component. Because let me see if I can find a diagram. That here's kind of an example. I mean, of a heat plume. There's lots of them. But, you can kind of see the heat rising, off this, and you can think of these as three power resistors right next to each other. Now, like I said, if you were to assume the ambient temperature is here, that's heat that's leaving the component. Okay, that's air that's rising, and, it'll probably leave the enclosure at some point, but even if it doesn't, still the most valid place to measure heat, would be right next to the component, right here. Not so close though that your sensor's going to heat up due to radiative heating, because if you're interested in is the temperature of the air, it wouldn't even be a bad idea to, like temporarily put something that blocks it, like a piece of cardboard or something, just temporarily to take your temperature measurement. So, you can kind of catch the temperature of the air real quick and then remove it real quick. I mean, like within a couple of seconds, however long it takes your thermometer to stabilize. But, just to block the radiative, because you're really not interested in what the radiative heating is. You want to know what the temperature of the actual air mass is, because it's the air mass that's going to be drawn into the component and heat it. Because this heat plume is rising, right? Well, that actually creates a partial vacuum, which draws cooler air in from the side that then bathes the components and effectively removes the heat as it rises. So again, you really want to measure, the temperature of any component laterally or underneath it if it's in free air. So you might have some power resistors, okay, mounted, just soldered to some like terminal blocks or something like that, to keep them away from your circuit board and other components. It's not a bad practice if you're really dissipating a lot of power. But in that case, you should measure the temperature again, maybe half an inch or so underneath the component, because that's the air that's most directly going to be drawn into the component to cool it. That's ambient air, all right? And like I said, if this were a sealed enclosure, a lot of this heat would spread around, so you should probably take your measurement after 20 minutes or so, just to see what the final temperature is. Don't just turn it on and take a temperature reading in 60 seconds. Wait for it to warm up in there. And make sure too, in your room, as far as ambient air is concerned, make sure your room temperature is in the right environment too. So if you're designing something that's going to go on the side of a building, okay, well then you got to take into account how much heat is going to be coming from the ground and the side of the buildings. It can get awfully hot. You'll get heat plumes off that too that are maybe going to go right into your enclosure. So that's going to really affect it. But the point is, you still want to take a measurement in your enclosure in its expected environment. So, and by the environment, I mean not the environment of the component. The environment of the component is your enclosure, right? But the enclosure itself can affect what the environment inside the enclosure is. Your outdoor temperatures, where you're going to use it. So if you're going to use it in a hot room or near a furnace or something, even if it's in its own enclosure, well, you still got to take that into account, obviously. So, you want to actually set, when you're testing it, in some kind of a temperature controlled environment that is similar to what you're wanting to work with. So, if you want to be really, really precise around it. Otherwise, if it's, just sitting around in the room, you can use like normal, 70-degree air temperature or whatever you want to use. But I'm just saying those are factors too. You got to take that into account. You got to think outside the box, literally. But what this guy was saying, and this is perfectly true, is that ambient temperature does not mean the outside temperature when you're specifying component temperatures. That's not what the manufacturer's talking about in their data sheets. So in fact, we can look at a data sheet here, like of this random component. I used to use a lot of these, by the way. They're actually okay little transistors. Let's see what we got here. Well, let me look this over so I don't waste your time. But yeah, and this, this transistor, will, you can see it's got, some thermal specifications like operating, storage and junction temperature. And like I said, oftentimes you'll see 150 degrees centigrade, as the maximum, TJ max, the junction temperature. But, I usually use these figures here when I calculate thermals with transistors, junction to case and junction to ambient. Junction to ambient you use if you're not using it with a heat sink, right? So that's your thermal resistance. So, it's 1 degree centigrade per watt. Alright, so basically if you had 1 watt, your transistor has 1 watt of power, that it's expected to be exposed to. Let's see. But I'm not going to go in too much detail on, on that. Let's just say your transistor is dissipating 1 watt, and you'll have to figure, that particular paradigm out, rather than me just making up an example. Because I was going to say, if you're using it as a switch, which I often did with these transistors, well, you got to know what the minimum voltage drop is, voltage across the collector emitter when the thing is on, and it's usually a certain very low voltage, usually a fraction of a volt, but it's, you got to multiply that by your current, right? Okay, so when the transistor's on, you've got, like, let's say half an ohm, and it's got 2 amps of current going through it. Okay, that's 1 watt dissipation. So, but that's just one example, a very brief example of where your power buildup may be coming from inside of a transistor. And that assumes all things are equal and the thing doesn't thermally run away or anything, which it still can do even as a switch, if you're not kind of careful. Because all transistors can thermally run away, if you don't have something that keeps it in check, you would want like some kind of resistor in series with it, for example, like a power resistor, like we were talking about earlier. So you may have one of those in there, for example. Sometimes that won't be, anyway, I'm just not going to go into it. You'll just have to figure that out for yourself, because it depends on your particular situation. So I don't want to draw this video out any longer than necessary. But at any rate, if you had 1 watt dissipation in your transistor, its temperature would rise by 62 degrees above ambient. Okay, but again, what is ambient? Well, ambient is the temperature you got to figure is, inside your case, again, like I was talking about, preferably underneath, if that's not possible, because let's say the circuit board, let's say the component, is mounted on a, horizontal circuit board, right? Okay, so your cooling air is actually having to come from laterally, from the sides. So you'd measure it as close to the circuit board as you can, probably. And that would even include if there are heat generating components under, mounted on the other side of the circuit board. So that's still going to contribute to your local heat for this component. So let's say we had this transistor, mounted on a horizontal circuit board, all right, with a bunch of other components and maybe other components on the side. You still want to take, the temperature kind of near, the base of the component, because that's your cooling air. But, probably a little above the circuit board. My recommendation would be, like half an inch, quarter of an inch or so, maybe half an inch above the circuit board, but also a quarter of an inch to half an inch away from the transistor itself. And, you want it to be close to the transistor, but if you have a heat sink on the thing, it can get a little more complicated, but still the same concept applies, that you still wouldn't want to measure the temperature of the heat sink itself. You want to measure the air that's going to be cooling the heat sink most immediately. So it would still apply, but if you had 1 watt in your transistor, it'll raise the temperature by 62.5 degrees. Okay, but that's above ambient. So if you measured your temperature right next to the, the component, here's your ambient curve, by the way. But if you wanted to measure it right next to the component, see, we're talking about 1 watt and ambient, this is the maximum allowable ambient temperature it can have. You can see right here, it would be about 90 degrees centigrade. Okay, so at that point, your junction temperature would be, 150 degrees centigrade. You never want it to go above that. You preferably don't want it to come too close to it, but you never want it to go above that. But so in other words, if you had a 90-degree reading inside your enclosure right next to the component and more or less underneath it, you're trying to measure the incoming air, basically that incoming air temperature can't be any higher than 90 degrees. So, and if you're operating at, let's say, 60 degrees, if that's what you measure or expect to be in your environment in that area, then, well, okay, you'd have that 62.5 degree rise above 60 degrees, so it would be 123 degrees. It would put it here, but that's still well below our TJ max, which is 150. So, now if you use heat sinks on it, you can get much better performance here. So, so this is the case temperature, is what it is. So this is assuming that a heat sink might be applied, when you use that figure. That's the only time you use that junction to case temperature. I really didn't mean to go into this subject, but but it's 1.56 degrees centigrade per watt. So for example, if you had 1 watt, your power transistor was dissipating 1 watt, like we just discussed. And again, this applies to resistors too, except resistors don't have a junction temperature, but but they do have their power limits too, like that guy was saying, especially in a power resistor. But 1.5 degrees centigrade per watt means the case temperature versus the junction temperature will rise by 1.56 degrees for a 1 watt temperature. Alright, so it's it's going to be 1.56 degrees hotter than the junction temperature, basically. But if you're using a heat sink, well, okay, you've got to take into account where the heat sink's bolted to it, your heat sink grease, and all these thermal resistances. But that's a subject of another video. But if you yeah, I just have a tendency to go off topic. I hate doing that. But yeah, if your transistor, we're dissipating 10 watts, well, that'd be 15.6 degrees, okay? But that's the temperature of the case. It's not the temperature of the ambient air. This is the temperature of the ambient air used without a heat sink. So that's about the only time you really use this figure, at least for me. That's the only time I've ever used that figure. This junction ambient is when you're using a component without a heat sink. And a lot of components, like, because almost all electronic components, including op amps and everything, have these temperature figures in them. So, usually you don't use a heat sink with most op amps, but sometimes power dissipation in an op amp can actually be an issue. So even like a 741, there are cases when, if you're pulling full load on it, that thing can overheat. So, you do still need to, like, glance at these and consider it, at least in passing, if you're, designing something you want reliable. I'll put it to you that way. Otherwise, you can just build your circuit and, and look at it with a thermal imaging camera or something and see how hot everything looks, which is what I'd mostly do with most op amps. But there are times when you've got to think about it. If you're really trying to draw a lot of the maximum current, which might just be 20 milliamps out of an op amp, it can still overheat. It can still exceed these parameters if you're not careful. So, it's something to take into account. So if you're having failures, you got components burning up, maybe you're drawing a little too much current out of that op amp. It may just be like 15 milliamps. Hey, it's rated at 20, but guess what? Your temperature environment's a little too hot. So it's melting your op amp basically. So, or at least causing it to misbehave big time. So, because a lot of these components, are drastically affected by temperature. So, you can run into trouble, even if you're not melting your component down. It can really not behave like you might expect it sometimes. So you gotta, you never discount thermal issues as being part of the problem if you're having problems. So, but basically, yeah, I'm not going to go in, there's lots of videos out there, on how to calculate thermals for transistors and all that. It's not that difficult. But the point I'm trying to make is, what is ambient temperature? And that's what I'm saying, because this is all, assuming, some kind of an ambient temperature. Okay, what does that mean? Well, that's what this video is about, is telling you, in my opinion, what it is. Now, in a case when you have forced air cooling, okay, which, you might have a fan in there or something like that, drawing, heat out of it. Well, forced air cooling is going to be upstream temperature. Again, I suggest, 1/4 of an inch to 1/2 an inch away from the component. Okay, but it's in the air that's going to cool the component, but hasn't yet. So if you've got forced air cooling, you want to kind of, measure it. Okay, you got a fan, let's say you got a fan that's exhausting air out of the enclosure. On the other side, you got some vents so fresh air can enter in. Well, you want to measure the temperature 1/4 an inch or so, in my opinion, on the vent side of the component, where the air is coming from, right? So, because that's what's going to be cooling the component, that's going to be your ambient temperature. So it's just a matter of thinking about it logically. But yeah, I still don't know what the standard specification would be. Sometimes these guys tell you what they define, but still what their definition is and how you're actually using it. I mean, it depends on how you're mounting your component, you know. So you've got to think about where the cooling air is going to be coming from in your enclosure, and it's not even a bad idea to do a little smoke test on it so you can actually see, you know, have a cigarette or something generating some very wispy smoke, um, you know, so you can kind of see, you know, how the heat and, you know, and the air is moving around that hot component. So, because even if in forced air, you know, you may be making assumptions about where the actual cooling air is, because maybe, you know, maybe that component is still so far away from the cooling air stream, it still might be coming from underneath on a, you know, let's say a circuit board that's vertically mounted with a transistor sticking out the side of it. You still may be getting most of your cooling air from the bottom, not the top, if it's out too far out of the airstream. So again, it's, you know, it's good just to be around there somewhere. But I still say, even in the case of forced air cooling, you still might be better off measuring the temperature always slightly below the component on a vertically mounted component. On a vertically mounted circuit board, I mean. So, you know, a component mounted to a circuit board that's vertical. So, but at any rate, that's my opinion. So, but it's just a matter of thinking through it logically. And um, so, but at any rate, if you haven't looked at Elliott Sound Products articles, are pretty interesting. So, you know, they're worth a read, even if you have been into electronics for, geez, 40 years or so like I have. So, anyway, cheers.